Sanctioned by Science and Engineering Research Board, funded amount of rupees 48 lakh 79,000, and Center of Technology Development and Transfer, funding amount of rupees 50,000, Anna University. He is also a deputy coordinator and one of the principal investigator in UGC projects of UGC projects for the university with excellence in biomedical engineering and instrumentation with the seed amount of rupees 75 crores. Currently, he is working on the project worth rupees 2.97 crores and 2.27 crores. He is a member of IEEE, Indian Laser Associations, SPIE, and Indian Unit for Patent Recognition Artificial Intelligence. Now, I would like to hand over the session to Dr. Sathiesh Kumar, sir, to give a deep insight on how to classify both the image and text using TensorFlow. Over you to sir.
Thank you, ma'am. Thank you for your introduction. So very good morning to all the participants. So I will just share my screen. Does the screen is visible?
Yes, sir. Is it visible?
Okay. So thank you. So today I'm going to present about text and image classification using TensorFlow 2.1 version. So first, let me start with a general introduction of artificial intelligence system. So artificial intelligence system is something like a system which is going to have a CPU, and the CPU is going to execute a program. So the program is going to be intelligent enough to do some important aspects. So ultimately, we are going to write a program which can sense, reason, act, and adapt to a particular situation. So it is not just like a normal program. So it is going to do some sensing, reasoning on the data, and act and adapt to a particular situation. So in artificial intelligence system, we have two major major subset, which is your machine learning. So in machine learning, again, we are going to write an algorithm where its performance gets improved as I try to expose more and more data. So when I try to increase the number of data, the performance of the algorithm or the performance of the machine is going to get improved. So in machine learning, again, we have another subset called as deep learning. So in deep learning, we try to make use of neural networks to make the predictions. So I'm going to concentrate on this deep learning systems. So especially neural networks. So in any machine learning algorithm, it involves 5 major steps. So the first step is the collection of data set. So when I talk about a data set, a good data set will result in good machine learning system. So here the data set, it requires 2 important parameters. So one is I should have as many number of data. Second one is I should have a variety in my data. So whenever we try to collect a data set, we should take these two things into our mind. So first thing is I should have more amount of data, and the second thing is I should have a variety in my data. So once I obtain the data set, I can divide the data set into 2 major categories. One is training set, another one is test set. So training set means this data will be used for making the machine to learn, whereas the test set will be used for evaluating the performance of the system, how much it has learned. So we need to divide this data set into 2 major categories. One is training data as well as test data. So training data, we use it for making the machine to learn. Test data is used for evaluating the machine, how much the machine has learned or how much good the machine is going to make a prediction. So whenever we talk about the split can be of different nature. Like some research groups, they work with 66% and 33%, 75-25, 80-20, 90-10. So there is no unified rule for this data split. So depending upon your application, you can choose your data split ratio. So you have to have this iterative process and you have to find which data split ratio is going to provide you the best result. So then you have to stick upon to that. So once I divide my data set into training and test data, the first step involved is your feature extraction process. So here I'm going to talk about two major applications. One is text classification as well as image classification. So in both the cases, what I can do is I can extract the features and I can give these features to a neural network, or I can give the raw data as it is to the neural network. So there are two ways in which I can do my prediction. One is I can give the raw data as it is to the neural network, or what I can do is I can apply some feature extraction algorithms, extract the feature from the data, and then use that features for your final training as well as test process. So the next two steps are training the machine as well as evaluating the machine. So these are the 5 major steps involved in our machine learning algorithm. So now let me talk about a very fundamental neural network. So a neural network is made up of 3 important layers: an input layer, a hidden layers, as well as an output layer. So the input layer here, this indicates an input layer, and here I have hidden layers, and here I have an output layer. So the input layers, hidden layer as well as output layer, it is going to be having neurons. So in the input layer neurons, the neurons are not going to perform any processing. It is just going to forward the information to your hidden layers. Whereas the neurons in the hidden layer and in the output layer is going to do some computation. So this you should remember. So first thing is, even though I have some neurons in my input layer, so this neuron is not going to perform any mathematical operation. It is just going to forward your input information to the subsequent layers. Whereas the neurons available in hidden layer and in output layer are going to do some processing. We will very shortly we will see what type of processing it is going to perform. So if I take an image, for example, if I take an image, let us consider this as an image. So let me specify the dimension as 8 by 8. So altogether I will have 64 pixels. If I consider this image as a grayscale image, if I consider this as a grayscale image, then I have only one channel. So my pixel intensities is going to vary between 0 to 255. Since I have 8 by 8 image, altogether I have 64 pixel intensities. I can use 64 neurons. So 1, 2, so like this it can go till 64 neurons, and each neuron can be supplied with the intensity of my pixel. So this is the intensity of first pixel. This is the intensity of second pixel. This is the intensity of 64th pixel. So like that I can go on. So this is a raw input given to your neural network. Second option is, instead of giving this raw inputs, I can extract the features. So I can take an image, give it to a feature extraction algorithm. Feature extraction algorithm. So it is going to give me the extracted features. So the extracted features can be something like 3 elements, 5 elements. So depending upon your feature extraction algorithm, the number of elements is going to change. So if I am going to take 3 elements as a feature, then I require only 3 neurons. I require 3 neurons to input that feature. So let me give the name as F1, F2, F3. Okay. So this is in the second type. So you have to decide, whenever you start with an application, you have to decide whether you are going to use the raw input as it is, or you are going to apply some feature extraction algorithms to extract the features. Then you are going to give that extracted features to your neural network. So you have to decide what type of input data you are going to feed it to your neural network. So what will be the main advantage of using a feature extraction algorithms? when I use a feature extraction algorithm, the number of features which I get or the number of elements in a feature vector is going to be small. So thereby the computation time will be greatly reduced. If I give a raw input, then more amount of time will be taken by the neural network to make a prediction. So that defines your input layer. So the input layer neurons, it is just going to forward the information to your next layer, hidden layer. So now I have an interconnection between two neurons. So each interconnection, so this is an interconnection between the neurons. So each interconnection is going to have some weight values. What is the role of weight? It gives the importance of the input, whether the particular input is important for the next layer neuron or not. If example, if I consider this weight W1 as 0, then this input is not going to get into the next layer neuron. If I specify the weight 1 equal to 1, then this input is going to pass on to the next layer neuron. So by assigning the weights, I can specify the importance of an input. So that is the role of having the weight functions. So once I give the input to the hidden layer neurons, now let us come to the hidden layer neurons. So this hidden layer neurons is going to do some operation. What operation it is going to perform? It is going to compute this function. So let us take a single neuron. So it is getting inputs x1 to xn, and we have set the weight values w1 to wn. It goes as an input to the neuron. So what the neuron does? Neuron computes this mathematical operation. Now let us see this mathematical operation. So here what we try to do is we take the summation of I equal to 1 to n xi ya, which means I'm going to take x1 w1 plus x2 w2 plus it goes on till xn wn. So this term is nothing but this term. So with this we add a bias term. So bias term gets added. So what we ultimately get is, so this entire term is added with bias term. So I will get a single value. When I compute this, I will get a single value. If I put some values for x1, w1, x2, w2, xn, wn, b. So if I set all these values, I will get a single value. So this is a linear function. So in order to make it non-linear, we give this data into a function which has a non-linear characteristics. So this has a non-linear characteristics. We will see what are the different functions available, which is popular in your neural network. We will try to discuss. So here I compute a linear computation, then give the data to a non-linear function. So this we try to say it as an activation function. Activation function. So what is the role of this activation function? It will decide whether the information has to pass on to the next layer or not. So our neuron is going to make a decision. It is going to make a decision whether the input has to go to the next layer or not. So that is what this mathematical equation represents. Okay, so now this neuron is going to do that computation, and it is going to decide whether the information has to be passed on to the next layer neurons or not. Same way, each neuron is going to perform the computation, and it is going to decide whether the information has to pass on to the next subsequent layers. Once the information passes on and reaches the final output layer, then I can make a prediction. So here we try to make a prediction y hat. So now we will try to see what are the different functions available. So we have different functions like linear function, sigmoid function, tan h function, ReLU activation function. So like that, we have numerous functions available. So this function, so for example, here sigmoid, tan H and ReLU activation function as a non-linear characteristics, whereas this linear activation function is a linear characteristics. So if I apply a linear characteristics to a data, then I will get a linear output. So it will not provide much interesting scenarios. So we will try to avoid this linear activation function. So we try to make use of non-linear activation functions. So here the popular activation functions are sigmoid, tan H and ReLU activation functions. So for example, if I do this computation, so here now I take this value, give it to a function. So it gives me, so for example here, summation I equal to 1 to n wi xi plus b. So let us assume this term, it comes about to be 2. So I'm going to compute f of 2. So let us assume that I'm going to find f of 2. So where f is a sigmoid activation function. So 2 comes somewhere here. So when I draw a line, so it has some value here. So what I can do is at 0, I can put a line. So this belongs to one category and this belongs to another category. So here my signal is 2. So it comes under 1. Let us take this one as 1. Let us take this side as 0. So 1 means the neuron will try to pass the information to the subsequent neuron. 0 means it will try to stop that input. So here if my f of 2, it comes about to be 0.8. So this lies in this right hand side. So the information will be passed on to the subsequent layer. If my f of minus 2, if I take f of minus 2, it comes somewhere here. So in that case, my information will be stopped by the neuron. So that is what the neuron is going to do the computation. That is how the neuron is going to perform the computation. So usually in the hidden layers, we make use of ReLU activation function. So what is ReLU activation function? For negative values, I have 0. For positive values, I have a linear output. So if my computation, this f of b plus sigma I equal to 1 to n wi xi results in some negative value, then my f of that x will be equal to 0. If it is a positive value, then I will get a linear output. So usually in a hidden layer scenario, we try to make use of the ReLU activation function, whereas in the output layer, we make use of sigmoid activation function for binary classification. If it is a binary classification, we make use of sigmoid activation function, or we use softmax activation function. Okay, so like that, our prediction is going to be obtained. So now we get an output prediction y hat. So this is a predicted value by our network. This is a predicted value. So we already know the ground truth value. So ground truth value is nothing but if I have an image, what the image contains, I know. So that ground truth value I know. So that I represent as y. So I try to compute the difference y hat minus y. So this is the predicted value. This is the actual value. So it gives me a loss function. If my prediction is wrong, then I will have a higher loss function. If my prediction is right, then my loss function will be minimum. So if my prediction is wrong, loss will be high. So what we try to do is, in order to minimize this loss, we try to perform do. I will try to take it as j. Loss function, I'm going to specify it as j with respect to do w. So I try to modify the weights. In order to minimize this loss function, I try to modify the weights in this layer. So let me repeat it once again. So first I give an input, goes, it gets propagated. I make a prediction y hat. It is getting subtracted with a ground truth value. This is the predicted value. This is the ground truth value. So we define this as a loss function. So in order to minimize this loss, I'm going to modify the weights in this layer, weights and biases in this layer, right? So what we do is dou J by dou W. If I modify this weights and biases, then certainly I have to modify the weights and biases of the previous layer neurons. If I modify this, again I have to modify the weights and biases of the previous layers. So this phenomena is called as back propagation phenomena. So I keep on updating my weights until my dou J by dou W. So my loss function is very, very minimum. So if it reaches minimum, I stop updating my weights. So that is how the neural network works. Okay. So here you can see that a typical loss function will be like this. If I have a single neuron with two input values and a bias value, so it makes a prediction. So I try to define the loss function like this. So along x-axis, one axis I have W1, another axis I have W2. So for example, if initially my loss is here somewhere, then what I do is I compute dou J by dou W1 and dou J by dou W2. So by computing this, I can check whether my loss function is going towards the minimum value. Okay. Once it reaches the minimum value, I can stop updating my weights. So that will be the optimum value of W1 and W2. So that is how the iteration will work on. That is how the optimizer is going to work on. So here in a neural network, there are two important conditions which you need to understand. One is a underfit model. Another one is a overfit model. So what do you mean by underfitting? If I don't have sufficient data, then our model is not going to learn much. Then it is going to have high training error as well as validation error will be there. So that is called as a underfit model. So if the network doesn't have much data to learn, then it is going to make lot of wrong predictions. So that we say it as underfit model. In the next extreme case, we have a overfit model. So in overfit model, what happens? If my data is more, then our model has learned many things, many parameters it has learned. Then what will happen is it is called as a overfitting model. We try to see some examples on this underfit and overfit models by doing some applications. Okay, so with this basic introduction about the neural networks, let me go to the application point of view. So I'm going to talk about text classification using TensorFlow. So text classification is a process of assigning tags or categories to the text according to its content. Based upon the content, I'm going to assign some tags, assign some indexes to the text. So that we say it as text classification. So it is the fundamental task in your natural language processing. So here I'm going to talk about IMDb movie review classification using neural networks. So movie reviews have been given by different persons. Based upon the movie reviews, we are going to say whether the movie is good or bad. So that is what we try to do here. So let me I'm going to open Google Colab. I'm going to show you a demonstration using Google Colab. So if you have a valid Gmail ID, you can easily go to this website collab.research.google.com. So here you can make use of this cloud environment, cloud GPUs for performing your machine learning algorithms. So here I'm going to open, I have a program which is saved in my drive. So I'm going to open a program. Okay. So this is a Google Colab environment, which is a cloud-based environment. So here in a Google Cloud, we have a lot of GPUs, TPUs available. So it is available freely for the user to make use of it. So we can write a code and we can execute the code in the Google Colab environment. So in order to use the GPU in the cloud environment, what you can do is you can go to this edit notebook settings. In notebook settings, you have the hardware accelerator. So you can select to use the local system, or you can use a GPU or TPU. So for this program, I'm going to make use of GPU. So I select the GPU. So save. So right now I have saved, and now I'm going to connect it to the GPU. So here I have an option called connect button. So if I press this, it will get connected to the cloud GPU. So it is getting connected. So now in this program, what I'm trying to explain you is a model we are going to design to classify the movie reviews. IMDb movie review data set is available. So from that, we try to take the reviews, and based upon the reviews, we are going to classify it, whether it is a good review or it is a bad review, whether the movie is good or it is bad. So we get a lot of positive and negative reviews are available in the IMDb dataset. We have about 50,000 movie reviews are available in this IMDb dataset. So out of this 50,000 movie reviews, we have about 25,000 reviews under training set and 25,000 reviews under test set. And this IMDb dataset is balanced. Balanced in the sense it has almost equal number of positive and negative reviews are available. Almost equal number of positive and negative reviews are there. Here I'm going to use a transfer learning method. So a transfer learning method is something like I have a network which has been trained, which has been optimized for a particular application. So optimized for a particular application in the sense already the weights have been updated and weights and biases are reached the optimum values. So this optimum weights and biases, I can use it in a new network so that I need not start it from the scratch. I can start it from the pre-trained weights and biases. So this technique is called as a transfer learning technique. So we have a network. So the network is trained for certain application so that the weights and biases are updated. So I have the updated weights and biases, bias terms. So this values, I can use it in a new network so that my computation time can be greatly reduced. So I'm going to make use of this transfer learning from the TensorFlow hub dataset. So now we will start our program. So first I'm going to import certain packages which is required for our program. So some basic packages like import function, division, print function, Unicode literals. So some basic functions. Same way for plotting, I'm going to import the matplot library. So in short form, I'm going to use it as PLT. So and I'm going to use a NumPy package, which is a very useful for doing matrix computations, array computations. Then I'm going to install TensorFlow 2.1.0 in the cloud environment. It is not on the local system, it is on the cloud environment. So how I can install is using this command, exclamatory mark. So let me make it a little bit bigger. So exclamatory mark pip install TensorFlow 2.1.0. So it will get installed in the cloud environment. Then I'm going to import the TensorFlow as TF. Then I'm going to use a pandas library, which is a data manipulation tool library. So in short form, we try to define it as PD. Then I'm going to use the TensorFlow hub for pre-trained models and the TensorFlow dataset for getting the IMDb movie review dataset. So IMDb movie review dataset is available in the TensorFlow datasets. So let me execute this. So when I execute this, you can see that right now it is getting installed in the cloud environment. Okay, so let it run. It will take some time for getting installed. So after getting installed, I'm trying to print the version. What type of TensorFlow version is installed? Then we try to check some parameters like whether the execution is going to be based upon graph based method or it is going to be a normal execution. So in order to check that, we use the eager mode. So in order to check the eager mode, we use this function tf dot executing eagerly, whether it is eagerly executing or it is executing using a graph based method. So then I try to check what is the hub version using this hub dot underscore underscore version underscore underscore. Then I'm going to check whether the GPU is available or not. Whether it is available or not, we try to see in the cloud environment. So it is installing. So I have already installed it. So it is saying that requirement already is satisfied. Okay, so still, yeah. So once I done this, you can see that when I print this, you will get information like this. Version is 2.1.0. Eager mode is true. Eager mode is true in the sense we are going to execute in a normal fashion. It is not a graph based execution. Then hub version, it shows same way it says GPU is available. So such information will be obtained when I execute this set of code. So after this, what I do is I'm going to load the data set. So from where I'm going to load the data set? I'm going to load the data set from TensorFlow datasets. So TensorFlow datasets, I have used the short form TFDS. So now it has executed. So we will execute this one. Okay. So now tfds.load function will load the dataset. So TensorFlow has a lot of datasets. So in that, I'm going to use the IMDb reviews dataset. IMDb reviews dataset, and I'm going to split the dataset into training as well as test function. For splitting the data into training and test, we give the split command. So here I have 25,000 reviews for training, 25,000 reviews for testing. So in training set, again I'm going to split it into two categories. One is for training and another one is for validation. So 15,000 images for training and 10,000 images for validation. So first let me take this split function. Here I have two categories, two important categories. So this is my training data. This is my test data. So here I specify test colon 25,000 means there is no starting point. So it starts from 0. So it goes from 0 to 24,999. So 25,000 reviews will be obtained in the test.
Excuse me, sir.
Yeah.
So you are doing this splitting of 50-50%
Yeah.
around. So is it a good, you can say, method? Because
Uh,
otherwise we generally go for 60 or 70 at least for training and rest for testing.
Ma'am, you please have note down all the questions. So at the end of the session, you please ask because
Oh,
I will just
okay,
first
sir.
complete my presentation. So please have a note of your question. So I will try to answer it at the last. Okay. So here I'm going to have my training data. So I'm going to in training data. I'm going to split it into two categories. One is trained data. So this is my trained data. This is my validation data. So in training data, I'm going to start from 0. I go till 15,000. So remember in Python, 15,000 means stop condition. 15,000 will not be included. It will go till 14,999. So 0 to 14,999. So again, in the validation data, I start from 15,000 till the end of the training data. I'm going to have the data. So that is how I split the data here. Then I specify the batch size to be -1. So if I specify the batch size to be -1, it indicates I'm going to have a full data set as a TensorFlow tensors. So I'm going to take, there is no batch size, right? So I'm going to specify it as -1, which indicates that I'm going to take the entire data set as a tensor, TensorFlow tensor. Then after executing this command, what we will have is we will have a train set here and a test set will be here. In train set, I will have train data and validation data will be available. So this data is in a tf.tensors format. It is in a tensor format of TensorFlow. So I am going to convert this array, TensorFlow array, into a NumPy array. So in order to do that, what we do is we use tfds dot as NumPy. It will convert your TensorFlow array into a NumPy array. So train data, validation data, as well as test data, I try to make it as NumPy arrays, because we are going to use lot of NumPy computations, lot of functions we are going to use using NumPy. So that is why I'm converting my TensorFlow tensor into a NumPy tensor. So I try to print the examples and see how many training examples are there, how many validation examples are there, and how many test examples are there. So when I execute this, now it will try to download the data set from the TensorFlow datasets. Then it will print and show me how many data are available in train data, validation data, as well as test data. Okay, so once the result comes, I will explain it. So let me go to the next one. So here I'm going to see how the reviews are going to look like. So from train examples, I'm going to take only the first 10. First 10 reviews, let us see what happens. When I execute this, you will get an output like this. You can see each line is a review. So in the first review, this was an absolute terrible movie, something, some person has written this review. So they have given a review about a particular movie. So here you can see that after executing this, you can find the number of training entries is 15,000, validation entries is 10,000, and test entries is 25,000. So we try to visualize the reviews, top 10 reviews, not top 10, first 10 reviews. So here I have first 10 reviews. Here one important thing you have to notice, each review is of different length. It is not of same length, right? So the first one ends somewhere here, second one somewhere there, third one somewhere here. So each and every review is going to be having different lengths. So this is one of the important aspect when you try to do any text classification. Next, we will try to see the labels, how the labels are looking like. So here, if I see, I'm going to take the first 10 labels. So when I execute this, you can see 0, 0, 0, 1, 1, 1. 0 means it is a negative review. 1 means it's a positive review. So we try to see whether the review is negative review or positive review. So this is the label, this is the data associated with your data set. Now let me try to build a model. Whenever we build a model, there are three important factors you have to consider when you do text classification. First thing is how you are going to represent the text. Because for a neural network, whatever you feed in to the input layer, it should be a number. It will not accept the string values. So I should have some methodology to convert the string into a number. We should have a methodology to convert the string into a number. Then that number can be given as an input to your input layer neurons. Then second aspect is how many layers you need to have in your neural network. Whether I need to have 1 layer, 5 layer, 10 layer for a particular application, how many layers I need to have. And the third important factor is how many neurons should be there in a layer. Whether I should have 10 neurons, 100 neurons, 1000 neurons, how many neurons should be there in each layer. So these three important parameters you have to consider while building a model. So in a text classification, first thing is you have to see how to represent a text. Whether how to convert a text into a number. Then only I can feed that input to a neural network. Second one is how many layers I should use in the model. Then how many hidden units or how many neurons should be there in each layer. So these things we need to understand to build a model. So one way of converting your text to numbers is by using the embedding vectors. So here is where we make use of the pre-trained model. So in a pre-trained model already with certain vocabulary, a model has been created. So if I give a string to that model, I will get the numbers as an output. So it is already available. So I try to make use of that pre-trained model in our application. So we try to gather the pre-trained model from this link. Google/tf2-preview gnews civil -20 dimension/1. So this is a model from TensorFlow hub. So in a TensorFlow hub, I have a embedding model. So the embedding model will take string as an input and it will give a vector as an output. So here the vector size can be varied. I can have a 20 dimension vector. I can have a 50 dimension vector. I can have a 128 dimension vector. Here this pre-trained model link is going to give me a 20 dimension vector. So for example, if I give a sentence, how are you? It will give me a 20 dimension vector. I'm going to teach TensorFlow. It will give me a 20 dimension vector. If I use this pre-trained model. Same way you can go to this TensorFlow hub. You can just type in Google TensorFlow hub. You can find a 50 dimension vector also available. 128 dimension vector is also available. So in that case, if you give how are you, it will produce a 50 dimension vector. In case of 128 embedding vector, you will get a 128 dimension vector. So I'm going to make use of this pre-trained model in our application. So first thing is I'm going to load the link where my pre-trained model is available. So here I have a link where my pre-trained model is available. So that I try to move it to a embedding. So now I'm going to create a layer which is called as a embedding layer. When I give a string to that embedding layer, what will happen? It will produce me a string output. So that is what we try to get here. So here I create a hub.keras layer. I give embedding. So I'm going to use this model. And what is the output shape? I need to get a 20 dimension vector. So I specify the output shape as 20. Input shape is empty, meaning my reviews can be of different length. I can't specify a input shape. I have so many words in a review that I can't able to say, because a particular review can have 10 words, another review can have 100 words. So my input shape keeps on changing. So we keep it as empty, whereas the output shape is defined. So my embedding layer should give a 20 dimension vector as an output. So I try to see how this layer works. Okay, so I try to take 3 examples from trained data, 3 examples. When I give it to this hub layer, here I define the hub layer. I give these 3 inputs to the hub layer. You can see that it is giving me, so this is a 20 dimension vector for first review. Same way, this is the 20 dimension vector for second review. This is the 20 dimension vector for the third review. For the entire sentence has been converted into a 20 dimension vectors. So we have taken only top first 3 in the trained data. In the trained data, I have taken only 0, 1 and 2. So for example, here this statement, the first statement, is converted into this array of numbers. Same way, second statement, this second review is converted into the second array of numbers. So like this, we convert the string values into a number format using the pre-trained model. So once I have done this, I can create a neural network model easily. So here I use a tf.keras sequential function because our neural network is sequential in nature. I have an input layer. After input layer, I have a hidden layer. After hidden layer, I have an output layer. It is sequential layer, sequential network. So we try to define tf.keras sequential. Then after initializing our object model, so first layer is going to be your string to number conversion, which is your hub layer. So I'm going to define the hub layer. Once I get the hub layer, then I'm going to use one hidden layer. So in one hidden layer, I'm going to have 16 neurons with the ReLU activation function. As I said earlier, hidden layer, we try to use ReLU activation function, whereas in the output layer, we make use of a sigmoid activation function, sigmoid or softmax activation function. If it is a binary classification, we give sigmoid. If it's a multi-class classification, we go for softmax activation function. So here I define my hidden layer with the 16 neurons, and we specify it as a dense interconnection. So dense interconnection in the sense the previous layer inputs, all the inputs will be connected to each and every neuron in the hidden layer. Then I have one output layer with sigmoid activation function. So that defines our model. So when I let me execute this. So till this we have executed. So this we try to execute, build a model. So here I try to see the summary. So here you can see the first layer is my keras layer, which is your hub layer. It has about something like 420 parameters are available. It depends upon the vocabulary set of the pre-trained model. Then I have a dense layer, which is a hidden layer. I have 16 neurons. So 16 neurons in the sense, how many parameters I need to have? I'm going to have here from this hub layer, I'm going to get a 20 dimension output. So this 20 inputs are going to go to each and every neuron. So how many parameters I will have? So I will have 20 into 16. So I have 320 weight values. So my keras layer has 20 outputs. So 20 outputs goes to each and every neuron in the hidden layer. So I have 16 neurons. So altogether 20 into 16, 320 weight values I have. Plus I have 16 bias terms because each neuron is going to have a bias term. So I'm going to add the bias values. So altogether I have 336 parameters. Same way in the output layer, I have only one neuron. So one neuron in the sense, the neuron gets the input from 16 hidden layer neurons. So 16 plus one bias. So altogether I have 17 parameters. So if I add all this, my network has about 4,373 parameters are available for tuning. Now, after defining a model, I need to set some parameters for the model. So here, parameters in the sense, what type of weight updation I need to do. So there are a lot of methods for weight updation, like stochastic gradient descent, ADAM, ADAMAX, ADA delta. So different types of optimizers are available. So here I try to specify what type of optimizer we try to use and what type of loss function I'm going to use. Since here I am going to work with binary prediction, binary class prediction. So we use binary cross entropy and what metrics I do require. I'm going to check the accuracy value. So I try to set the parameters. Once I set the parameters, I can do the training process. How to do the training process? Using this model.fit function. So model.fit function will do the training on train examples and train labels. I give the training data here. So we try to specify the batch size. So batch size is very important because how often we need to update the weights. If I specify 512, then for every 512 train examples, the weights will be updated. If I don't specify a batch size, then for every example, the weight will be updated. So here, if I specify a batch size of 10, then for every 10 examples, weight will be updated. Then epoch, I try to specify it to be 20. So what do you mean by epoch? Epoch is nothing but I give the input data in the data set, show it to the network completely. For example, in my data set, I have some 100 examples. So exposing this 100 examples to a network is called as one epoch. So if I can expose the data again and again, multiple number of times I can expose the data to a network. So that we try to specify it as epoch. So here I'm going to expose my data 20 times. Same way, I have a validation data. I give validation examples and the validation labels, and verbose function is just for printing the output, how my output will look like. So when I execute this, you can see it has started training on 15,000 samples, validating it on 10,000 samples. So for the first epoch, it is running. So it shows loss, accuracy, validation loss, and validation accuracy. Right? So this is for every epoch it is trying to give. So this loss is nothing but training loss. During training process, the loss obtained is shown here. Same way during training process, what is the accuracy which we obtain? Same way during the validation process, what is the loss and accuracy we obtain? So here you can see that it is not constant for all the epochs. As the number of epoch increases, you can see my training loss keeps on reducing. It keeps on reducing as I go for more number of epochs. But what happens to the validation loss? Here you can see initially it is reducing. It is reducing. Validation loss, it is reducing. Okay, so here for this example, it keeps on reducing. So there will be a situation in which my validation loss will keep on reducing. And after some time, what will happen? The validation loss will start increasing. So that is the point of overfitting. So we can identify a overfitting model by that scenario. So in overfitting model, I have a training loss which keeps on decreasing, whereas validation loss, it will decrease for certain number of epochs. After some time, it will start increasing. So that is the point at which my overfitting happens. So we try to evaluate the model and see. So here it shows about 86% accuracy. So we try to plot the graph and we try to see how it looks like. Okay, so this and all is just for a plotting of accuracy. You can see here my training loss and validation loss. So x-axis is epoch and y-axis is my loss function. This is what I'm trying to say. So here what happens? My training loss keeps on reducing. Whereas what happened to the validation loss? It reduces and it is not reducing that much. So there is a deviation here. So this point is where my model try to overfit. So this is an unwanted scenario. So my validation loss also should decrease, but what it doesn't decrease that much as that of your training loss. So I can also plot the accuracy curve and we can able to see. Right. So this is regarding your text classification. Next, we will move on to image classification. Okay. So here also let me connect it to a Colab environment. So here what I'm trying to discuss is we are going to discuss how to classify images, a two-dimensional data. So here I'm going to use a fashion MNIST data set. So what it has clothing like a shirt, pant, sneakers, boots. So like that, we have lot of clothing information in the fashion MNIST dataset. So it has about some 60,000 training images and 10,000 test images are available in this fashion MNIST dataset. It has about 10 classes of clothing. Then each image, each data is going to be of 28 by 28 pixels. And each image is going to have a ground truth value. So the ground truth value is specified in terms of IDs. It varies from 0 to 9. So I have 10 classes. So each class has been labeled as 0 to 9. So class 1 will be labeled 0. Class 2 will be labeled 1. So like that it goes on. So class 10 will be labeled 9. And the pixel intensities are going to vary from 0 to 255. So this data set has a grayscale image of size 28 by 28. Pixel values vary from 0 to 255. In training, it has about 60,000 training images, 10,000 test images. Right? So now we try to classify this images using TensorFlow. So as usual, we try to install the TensorFlow 2.1 in cloud. So already it has been installed. Okay. So after installing, I'm going to import some certain packages. So these are the basic packages which we try to import in all the functions, all the programs. Then after installing, I try to import the TensorFlow as TF. Then TensorFlow as an advanced machine learning package called as Keras. So TensorFlow acts like a backend and Keras sits on top of the TensorFlow. So TensorFlow is going to be a backend and Keras will be the front end. So it has a lot of machine learning libraries available. Same way, I try to import the NumPy function for doing matrix operations, then matplotlib for plotting the data. So then I try to print what type of version is being available in the cloud environment. Okay, so still it is executing. So we'll move on to the next one. So now from Keras package, previously I have shown you to get the data set from TensorFlow. Now I will show you how to get the data set from Keras. So in Keras package, I have a data set called as fashion MNIST data set. So that data set we try to define using this variable, and using the load function, I try to load the data from Keras package. And it gets loaded into train images, train labels, test images, and test labels. So train images and test images are the data. Train labels and the test labels are the ground truth values. Okay, so it has completed. So I'll import these packages. Okay, it says 2.1.0. Now I'm going to load the data set into this training set as well as test set. Now I'm going to define the class names, because here in training labels and test labels, the labels will be in the form of a number 0 to 9. So I have to say what is 0, what is 1, what is 2. So for that we define the class names. So first class, it is going to be t-shirt, second class trouser, pullover, dress, coat. So like that I have 10 classes. So I have to associate each label with this class. So label 0 means it is t-shirt. Label 1 means it is going to be trouser. Label 9 means it is going to be ankle boot. So in order to do that, I initialize an array with this class names. Now let us print how many images are there in the train data, in test data. We try to see using this dot shape function. Using dot shape function, we try to see how many data are available in the training set as well as test set. So when I execute this, you can see here it says 60,000, 28, 28, which means 60,000 training data are there, and each data is going to be of 28 by 28 size. So second one is I'm going to print the labels. How many labels are there? 60,000 labels. Then how these labels will look like? As I said earlier, the labels will have numbers 9, 0. So 9 means it is ankle boot. 0 means it is t-shirt. So each and every image is having the labels in the form of a number. Same thing I'm going to do it for test image also using shape function, length function, and the test labels will give this information. 10,000 images in the test data, 28 by 28 is the image size. Then the labels are given here. Now let us plot it and see how it looks like. So I'm going to plot using plot figure. I'm going to plot train image second one. I'm going to plot it and see. So if I plot it, you can see it is something like a top. So if I change the value, so let us see the first data, what it is. So it is a boot. So if I take something like 10, so it is something like a shirt. So we try to plot it and see what type of data is available. Then I try to normalize the data. So in order to normalize the data, find the maximum value. So our image is a grayscale image. So the maximum value will be 255. So divide my data by 255 so that you get a value between 0 to 1. So we can normalize our data. Thereby I get a value between 0 to 1. So now what I do is I use some plot function again. So this is just for illustrative purpose. So I try to take 25 images and try to plot it and see. So here you can see the 25 images. First image is angle boot, t-shirt, dress. So like that we have 25 images. We try to plot it here because here I have specified the range value as 25. So it will take from 0 to 24. I try to move this value, train images of 0 to 24 so that I get this images. Okay. Participant, please mute your mic. Thank you. So next what we do is we create a model. So here in the model, we try to import the sequential function. Again, the neural network is a sequential network. So I make use of the sequential function. So here the very important thing is our neural network will accept only one-dimensional data, whereas our image is a two-dimensional data. So first thing what I have to do is I have to convert this two-dimensional data into one dimension. So what we do is we incorporate a flattened layer. So the flattened layer, what it will do, it will convert your two-dimension data into one-dimension data. So what is the size of our input image? It is 28 by 28. So 28 by 28 in the sense, how many elements will be there? So 28 into 28, I will get about 784 elements. So my vector after flattening will have 784 elements. So this 784 elements, I'm going to give it to a hidden layer with 128 neurons. And the hidden layer is going to have a ReLU activation function. Then finally, I'm going to have a 10 neurons because my output class is 10. So in my output layer, the number of neurons is going to be 10. So here I define a softmax activation function. Since it is a multi-class classification, previously we did binary class. In text classification, we did binary classification. So thereby we used a sigmoid activation function. So here we use multi-class classification. Thereby I use the softmax activation function, which means each image will have an array of probability score. A single image will have an array of probability score. It will have 10 values. So the first value will be the probability score of the image on class 0. Second value is probability score of an image on class 1, class 2, class 3. So like that I will have 10 values. So that is the role of having the softmax activation function. So we try to define the model and we try to see how it looks like using model summary function. So here, as I said, in the flattened layer, the output of the flattened layer will be 784. My input is 28 by 28, two-dimensional image, but I get a 784 element. one-dimensional image. Then I have a dense layer with 128 neurons. So in 128 neurons, I'm going to give this 784. So how many parameters will be there? So 784 into 128. So this many number of weight values I have. Plus I have to add the bias term. So for 128 neurons, I have 128 biases. So I add 128 biases. So altogether I have 1,480 parameters for this layer. Same way in the output layer, I have 10 neurons. So how many inputs I get for this each and every neuron? 128. So it will be equal to 128 into 10. So altogether I have 1280 weight terms. Plus I add 10 bias values because for 10 output layer neuron, I have 10 bias terms. So I add 10 bias terms. So it will be equal to 1290 parameters. So if I add both these values, I get 1,770 parameters I need to tune. Next, I try to compile. So compile is something used for setting the parameters for the model, like optimizer, how I should update my weights. So the most popular optimizer is your Adam optimizer. So we make use of this Adam optimizer. Then last, since it is a multi-class prediction, so we use a sparse categorical cross entropy loss. And the metric which we use is accuracy. So this is a parameter setting for the model. Next, I try to do the training process using model.fit function. I give train images, train labels, then I train it for 10 epochs. When I run this model, you can see now it is training on 60,000 samples. So the first epoch is running. So it shows both loss as well as accuracy. Remember, this is training loss and training accuracy. Here we have not used the validation set. So we don't get the validation loss and validation accuracy here. Now it is running for the fifth epoch. So let it complete till 10 epochs. Okay, so now it has completed. You can see it has obtained an accuracy of about 91%. 91% accurately it has been predicted. Then I can use the trained model for testing. So by using model.evaluate, I can check how well the machine has learned. So here it is training for 10,000 images. So it gives a text accuracy of about 88% is that. So here this completes our machine learning. So now let us try to understand what is the role of this softmax activation function. So I'm going to predict the test images. The prediction values will be available here. So this prediction will have all the 10,000 predictions. For 10,000 images, 10,000 predictions will be there. All the 10,000 predictions will be available in this prediction variable. So we try to print the first prediction alone. Prediction of 0 alone, we try to print it and see what happens. So if I print it, you can see that for the first image, my prediction returns like this. You can see how many values are there: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 values are there for a single image. So this is what I tried to specify earlier. So for each image, I get a probability score array. So I get 10 values. In this 10 values, so this is the probability score for my input image for class 0. Same way for class 1, class 2, class 3, class 4, class 5, like that it goes on till class 9. Now in this probability scores, I have to find for which class I have maximum probability. So here if I see it is 10 power minus 7, 10 power minus 10, 10 power minus 10, 10 power minus 12, 10 power minus 9, 10 power minus 3, 10 power minus 7, 10 power minus 3, 10 power minus 9. Here I have 10 power minus 1. So this is the maximum value. So I obtain a maximum probability score for class 9. So my predicted value will be 9. So we try to find where is my, in which position I have maximum score. So that I try to find using np.argument marks. So I try to say what is my predicted value, and we already know the ground truth value. Okay, from test labels of 0, I get the ground truth value. So here it says my prediction is also 9, my ground truth value is also 9. Now let us plot some graphs and we will try to understand it. So here this function is used for plotting the image input data. Input data we try to plot it. So here I use a plot.im show. I give the input image and use some color map to plot the image. And I'm going to set some colors. If my prediction is equal to ground truth value, I set it to blue color. If my prediction and ground truth value are wrong, we use red color. So this is just a plotting function. Same way I'm going to plot the probability score. So the probability score is going to be plotted using this plot value array. So here I'm going to use a bar graph to plot the values. It takes 10 values because I have 10 classes. So I'm going to have 10 values along x-axis and I try to plot it and see. So for example, let us take, I'm going to take the first example. Okay, 0. So I'm going to take the first example. I'm going to send it to the plot image function and plot the bar graph. Both the things I'm going to plot and see. So when I plot it, you can see that this is the image. Angle boot is the predicted value. Ground truth value is also angle boot. So predicted value and ground truth value are same. So it is 100%. It is saying it is angle boot. It is correctly predicting. So here you can see along this, I have 10 classes. This ninth class in the sense it starts from 0 to 9. So 9, I have 100% probability score. Now let us change the image and see. So let us take second image. You will see what happens. Here also, this is the image. My predicted value is trouser. Ground truth value is also trouser, 100% matching. So the label here is the trouser. It has a blue 100% value. Let us take some other image where I can find something like a variation. Okay, so we will take some other one. Okay. Okay, so here you can see that I have 97% accuracy. 97% it says one class, and there are some other classes also. Some small values are being assigned. So like this, we can see the probability scores. Here you can see this is a wrong prediction. Okay, so here red color indicates a wrong prediction. So here my prediction is full over, but the actual ground truth value is quote. So 67% it says it is full over. Okay, but that is wrong prediction. This is the quote which is indicated in blue color. This is the right value, but this it has lower probability score when compared to full over. Now I try to see, instead of seeing one by one, let us visualize multiple images. So I take number of rows 5, number of columns 3. So altogether 15 images we try to plot and see. So I send it to the same function. You can see that this is the first image, this is the probability score. Second image, probability score. So like that it goes on. So here you can see in this case, my prediction says it is sandal, but my ground truth value is sneaker. So it is 77%. It is saying sandal. So this is sandal, but the actual sneaker is available here in blue color. So this is regarding your image classification using TensorFlow. So with this, we will stop. So if you have any queries, please let me know. Thank you.
Sir, please tell me how the feature extraction has been done in the deep neural network.
So here we have not done any feature extraction, sir. We are giving the raw pixel intensities directly to the neural network. If you want to do some feature extraction, you can always apply some. If you want a color feature, then you can apply color histogram or color channel statistics algorithm. If you want a texture information, then you can go with the heraldic texture algorithm or local binary pattern or histogram of oriented gradient. So like that, we have many feature extraction algorithms depending upon what type of feature you require. So you apply that algorithm, you will get a feature vector. Then that feature vector, you can give it to the neural network.
Okay.
Sir, the same.
And one more question, you are using the sequential
Yes.
neural network. So for the back propagation or the feed forward, we have to change the
No,
function?
sir. So this is our optimizer we try to specify. So optimizer is nothing but it will update the weights and biases. So this updation of weight and biases will happen in the back propagation phase. So it is a back propagation neural network. What we are talking about is back propagation neural network.
Sir,
you, sir.
there's a question regarding the text classification.
Yeah.
So what features we have, what features are extracted, what features are data fed into the neural network during text classification? When you have used the pre-trained model, what are the features that are fed into the neural network?
Okay. Here in text classification, what we have done is, so it is, I will just explain with a slide. Okay. So here, what we do is, I have an embedding layer. Okay, so I give some sentence. How are you? Okay, some sentence I'm going to give.
Yes, sir.
So depending upon what type of pre-trained model I have here. So for example, if here in our example, we had 20 dimension model. So it will give me a 20 element vector. Right? So it will give me 20 element vector. So how this happens in the sense, in the normal model, each and first our sentence will be divided. For example, how are you? We try to divide this sentence into tokens. So this we call it as token. So this is token 0, token 1, token 2. Then each token will be assigned with some numbers. So already I will have a dictionary. So I will have a dictionary with some vocabulary. So for example, I can have something like 50,000 words can be there, or 1 lakh words can be there in the dictionary. So for each word, we try to put a number. So out of this 50,000, I can put 1, 0, 1, 2, like that. It goes on till 50,000. Right? So now I try to match it. So how belongs to which number here? So if it is coming like 20, I will put 20 here. Or
Okay.
it belongs to which number? If it is some 112, I put 112. So U means 144 means 144. So like this, we try to convert it into a number. So here in a movie review, what happens? My review one can have some 100 words, right? Review 2 can have some 1000 words. Then what happens if I do like this? I will get 100 elements here. Same way in the second case, I will get 1000 elements. So converting this 100 elements or 1000 elements into 20 elements will be done by this embedding layer. So embedding layer will convert this 100 words or 1000 words, whatever the length, it will be converted into a fixed number format. So all the outputs will be of 20 dimensions if I use that pre-trained model. So that is what happens in your text classification.
Okay, okay, sir. Okay, thank you.
Okay.
So one more question regarding the image classification.
Yeah.
So you have the 9 class label, right? In
Yeah.
string format.
A 10,
So
10 class label. 10 class label
10,
start
0
from
to
0
9.
to 9. Yeah.
Yeah. So which technique you have applied to convert the class string label into numbers?
No, here in this Keras data set, so the ground truth value itself, it is directly in terms of numbers
Okay, in Keras.
in Keras. So I have loaded that fashion MSD data set from Keras library. So
Okay.
there already it is available in the form of numbers. So in order to represent it as a string, I try to put the string values as class name. Class name, I try to put shirt, trouser. So like that, we try to define it.
Okay. Okay. And so next question, you have used the sparse categorical cross entropy loss.
Yeah.
So what is the difference between the categorical cross entropy loss and the sparse category? So why we have used here in multi-class problem sparse category?
So sparse in the sense our loss function, it is somewhat scattered in nature. Okay, it is not just like a fixed values of loss. As I keep on training multiple images, what will happen for each addition of a new input, my loss will keep on varying, and this loss function will be something like a scattered grouping. If I try to take for each sample, what is the loss? If I try to plot it in a graph, it will look something like this. So for example, if I try to take, so first image, my loss will be here. Second image, loss will be here. So like that, it will be something like a scattered nature.
Okay.
So what we try to do is we try to take this as a cluster, try to find the centroid value, and this we try to use it for weight updation. So that is why we try to make use of sparse categorical cross entropy loss.
Okay. Thank you, sir.
Yeah. Any other queries?
Sir, if we are not applying this cross entropy or loss function in the optimizer, what will happen to that output, sir?
Your weights will not be updated. So what will happen is, here initially what you do is you give inputs, you assign some input random weights. So let me take it as r1, r2, r3. So you put r3. So same way bias also, here in this layer I try to take it as b1 for simplicity. Same way in this layer I try to take it as b2. In this layer I try to take it as b3. So you will initialize this values r1, r2, r3, b1, b2, b3. You try to make it random. So your input propagates. You will make a prediction. You will get a loss, right? So loss is nothing but y hat minus y, predicted value minus ground truth value. So you will get a loss. Then for this loss, you will attain an accuracy. It will stop at that point. Right? If you don't have the back propagation phase, then there is no chance of minimizing this loss. This loss will not get minimized. If my loss is not getting minimized, I will not have a improved accuracy. Accuracy will not improve. If you don't do this back propagation phase, then you will have a fixed loss. Means you will have a fixed accuracy. Fine.
Super, sir. Sir, one more question, sir.
Yeah.
Is there any limit for fixing the epochs, or is there any technique for fixing the epochs, sir?
Okay. So regarding epoch, what we do is you have to plot this graph. This is very, very important graph. So along x-axis, we put epoch. Along y-axis, I try to take loss. Okay. So for any model, what you do is you try to plot this loss function versus epoch. So here for training and validation, I'm going to plot it. So training, usually it will be like this. So as the epoch increases, loss will keep on decreasing. Whereas validation, what will happen is, if I try to plot it for validation, it will reduce and suddenly it will start increasing like this. So this plot will indicate whether my model is overfitting or not. So till this point, my model works fine, right? My training loss decreases, my validation loss also decreases. So it is working fine. So suddenly what happens? my training loss decreases, but my validation loss increases. So this region, we say it as overfitting model. So we should never overfit the model. So overfit the model in the sense it has learned too much. So thereby it is following the input data. Then if I give a new data, new test data, it will not work. So in order to avoid this overfitting, we have something called as regularization rate. So I can add for my loss function, I can add this regularization parameter so that my validation loss can be reduced. So that is the role of having your epoch. So you have to plot the number of epochs and see where is my model overfits. At that epoch, you have to stop. And this is not a constant value. Depending upon your application, the number of epochs at which your model overfits will vary. Fine.
Thank you, sir.
So one more question.
Yeah.
So for multi-class problem, if we have class imbalance problem,
Yeah.
then what is the good method that applying the class imbalance problem technique before train or test split, or after train or test split?
So for class imbalance, so class imbalance in the sense in certain classes you have more number of data and certain
Yeah.
classes you have less number of data.
Data. Yes, sir.
In that case,
So if we are going to apply the class imbalance technique, then it is a good method before applying the train test or after train test splitting. So I'm confusing in this.
no, if anyway, first you have to do the train test split. Then only you have to give the data to your model.
So then it is the technique will apply on the train data.
Yeah. Anyway, since your classes are having variation,
Yeah.
in your training set as well as in the test set, you will have that variation will be there.
Yeah. So if we apply after train or test, then the after train test split, then the technique will apply on the train data, and the test data will remain same. Then the result have a lot of variation.
Please come again. I couldn't get you.
So if we apply the class imbalance problem after train test split, then the class technique imbalance problem will apply on the train data, right, after splitting. So when I use the test data, though the result is of variation, train and test, that because the test data is before applying the class problem and the train data is after applying the class label technique.
Okay, I'm not sure about that, whether it will work out or not. I don't know.
Okay.
So I'm not able to answer this.
Okay. It's okay, sir. Thank you.
Sir, good afternoon, sir.
Good
Sir,
afternoon. Yeah.
Sir, can you give me some resources, sir, about basics to learn these neural networks, sir, basics of neural networks?
You can just go to tensorflow.org. So
Okay, sir.
in tensorflow.org, you have something called as a learn tutorial, something will be there. So in that, all the applications and what are the functions available in TensorFlow, everything has been listed. So the material, whatever I have taken, it is from the tensorflow.org website. So I have done some small modification and I have just made it such that it is very easy for the audience to understand.
Okay, sir. For deep learning concepts, sir. For deep learning concepts.
For deep learning, neural networks as well as your convolutional neural networks. So a lot of tutorials are available in tensorflow.org.
Okay, sir. Thank you so much, sir.
Okay. Any other queries?
Sir, in the beginning, you told about the transfer learning.
Yeah.
But the data set you have used only one, sir? For training as well testing, you have used the same data.
No, pre-trained model is something different, ma'am. So actually, pre-trained model means, for example, let us consider a model. So M1. So I'm going to give some data. It is going to give me some output, right? So in order to here, it will also give some loss function. So I will try to reduce this loss. Okay, I try to update the weights as well as I try to update the biases, right? So we try to do this, and optimize the weight value. So I try to identify the weight as well as biases for this model. Okay. So now I create a new model. So let us take a new model. So for this model, I'm going to give a input data. Then in order for this model to train, I have to initialize weight as well as bias. Usually what we do, we initialize this weight and bias randomly. Instead of initializing weight and bias randomly, I'm going to take this weights from model 1. Weight and biases, I'm going to load it here. Okay, instead of random initialization, I'm going to initialize the weights of the new model from the already trained model. So that is why we say it is pre-trained model. Already it has been trained to get the best result. We use that parameters in the new model. Then I try to find the output. Again, I can try to modify. So here also I will get a loss. So let me take it as L1. So I take dou J by, dou L1 by dou W, comma, dou L1 by dou B. We try to update. This is called as a pre-trained models.
Thank you, sir.
Okay. Any other questions?
Participants, any other questions?
No, ma'am.
Yeah, thank you. Thank you, sir, for your outstanding presentation done on classification using TensorFlow platform. We are grateful for the time and effort you took to share your knowledge on neural network. Thank you, sir, for accepting our invitation. Once again, thank you, sir. Have a happy learning.
Thank you, ma'am. Thank you.